Hello, and welcome to this lesson where we're going to take a short break from all those videos you're watching on doing the Laplace transform mathematically to kind of take a quick look at how we're actually going to start to use the Laplace transform in our circuit analysis techniques. So we're going to take a look at an example involving a parallel RLC circuit and see how we can sort of create that long, kind of nasty node voltage equation that you would have used in your Circuits 1 class to solve for the voltage. And we'll see how we can really quickly just use the Laplace transform to flip it, do some really simple algebra, and then flip it back to get our voltage. So let's just get right into it. So let's consider a parallel RLC circuit that's got an independent current source that we'll just call IDC. It's got a switch that's open, or that will open at t equals 0. It's got a resistor that for now we'll just denote as R, an inductor that for now we'll just denote as L, and a capacitor, C. And it's got an output terminal. And our goal is to just figure out what is the voltage on the terminals as a function of time. So to do this, we first need to set up our single node voltage KCL equation. So I'm going to write that out. Set up a node voltage, or KCL, equation. So we'll start with the current, IDC. Now since the switch is there, we'll actually model the switch as just IDC times a unit step function. And that's equal to, let's see, the voltage across R is just going to be V of t over R, plus the current through the inductor. Remember way back to your Circuits 1 class, that we had this expression, 1 over L times the integral from 0 to t of V tau d tau. Plus the current through the capacitor is just C dV dt. Now what we need to do is apply the Laplace transform. So I guess in Circuits 1, we would take this equation and try to solve it out, right? It would be a sort of messy, hairy, algebraic thing. But as we'll see by applying the Laplace transform, once you're comfortable using the Laplace transform, it's actually a lot simpler to solve these sorts of circuit equations. This is why we take the time to learn it. So let's say apply the Laplace transform. So let's do it kind of piecemeal so we can see the different components. Now we're just going to go and look up these different things in our Laplace transform table. So let's say, remember that the Laplace transform of the unit step function is just 1 over s. So this expression, IDC times ut, will just become IDC over s. Next up, if we're looking at Vt over R, this one's pretty simple. Oop, wrong color. The Laplace transform of V of t is just V of s. So V of t over R will just become V of s over R. Next up, in the second Laplace transform table in the textbook, you'll find this expression, the Laplace transform of an integral 0 to t of f of x dx is equal to just f of s over s. So that simplifies, actually these don't equal, they're being transformed. So that expression 0 to t, or excuse me, 1 over L of v of tau d tau is going to just become simply v of s over s times 1 over L. And then finally, the Laplace transform of d, oh, that's a mess, the derivative of a function with respect to t, or function of t with respect to t, just becomes this, s times f of s minus f of 0 approached from the negative side. So that means that our c dv dt is going to transform into c times s times v of s minus v of 0 negative. So there's all of the little pieces, remember, so we just went and looked each of these up in the Laplace transform table. And so now we're ready to write out our whole Laplace transform expression. So let's see, we got I dc over s is equal to v of s over r plus 1 over L times v of s over s plus c times s v of s minus v of 0. So that's the voltage. V of 0 is the voltage in the capacitor at t equals 0. Now notice that we were at DC conditions with the circuit closed, and we had this inductor sitting here, which means that before the switch flipped, that current was just sort of shorting through the inductor, so there was no current flowing through the capacitor, which means there was no voltage on the capacitor. So that means that this voltage goes to 0. And we can simplify a little bit. So we can say that we have IDC is equal to, let's factor out all of these VS's. Because remember, we're trying to solve for V of t. So if we factor out the VS, we get 1 over R plus 1 over SL plus S times C. Oh, and that's IDC over S. Next up, we need to solve for VS. So that's pretty simple. That's just IDC over S times all of that, 1 over R plus 1 over SL plus SC. We can distribute that S into the expression, which gets us V of S is equal to IDC over S over R plus just 1 over L, because the S is canceled, plus S squared C. Now for algebraic reasons, it's usually a good idea to try and isolate this S squared by itself to make it quadratic. So that's what we'll go ahead and do. We'll factor out the C, and we'll get a final expression here for Vs is equal to I dc over C times S squared plus S times 1 over RC plus 1 over LC. And as you can see, once we apply some values to this, it's going to make it a pretty nice and neat quadratic equation that we can pretty easily solve. So if we want to find V of t, well, all we have to do is just apply the inverse Laplace transform on Vs to get Vt. So that's what we'll go ahead and do. Let's go ahead and apply some values to it to make it an example. So we've got, let's set IDC equal to 24 milliamps, R equal to 400 ohms, L equal to 25 millihenries, and C is equal to 25 nanofarads. So if we take all of those values and plug them into our expression for Vs, we'll get, let's see up top here, 24 times 10 to the negative third over 25 times 10 to the negative 9 over s squared plus s times 1 over 400 times 25 times 10 to the negative 9 plus 1 over 25 times 10 to the negative 3 times 25 times 10 to the negative 9. All right, bunch of big messy expressions, but if you punch all of that into your calculator, what you'll get is V of s is equal to 960 times 10 to the third over s squared plus s times 100,000 plus 1.6 times 10 to the 9, big old number, times 10 to the 9. And now we've got a quadratic equation here that we can solve. You can plug in your calculator, plug in Wolfram Alpha, whatever you want. But when we do that, that factors to be, we still got the 960 times 10 to the third hanging out on the top. So that'll be s plus 20,000 times s plus 8,000. So what's going to happen next is that we're going to choose to not care so much about that 960 times 10 to the third. Right, when we're talking about the Laplace transform, as we move forward, we're going to be really more interested in sort of the frequency, the time domain response of our signals. So what we can actually do is sort of cheat a little bit and say, let's break this up. We know that this is going to be equal to some constant over s plus 20,000 plus k2, some other constant over s plus 8,000. And with these two equations, we could solve for k1 and k2, but we don't need to because that's not the important part right now. But what we can do is now take the inverse Laplace transform to find our v of t. So v of t is equal to the inverse Laplace of v of s, which, due to the rules of addition and multiplication, mean that we can take these separate. So that's the Laplace transform of k1 over s plus 20,000, the inverse Laplace transform, plus the inverse Laplace transform of k2 over s plus 8,000. And we can also factor out anything that doesn't have an s associated with it. So let's say vt is going to be equal to k1 times the inverse Laplace of 1 over s plus 20,000 plus k2 times the inverse Laplace of 1 over s plus 8,000. Now, if you go and look at the first Laplace transform table in the textbook, you'll see that the inverse Laplace of 1 over s plus a is equal to e to the minus aat. So we can now write out our pseudo-final answer. We won't worry about those constants, but by applying the inverse Laplace transform, we know that the voltage as a function of time will be k1 times e to the negative 20,000 t plus k2 times e to the negative 8,000 t in volts. All right. So hopefully you saw that by applying the Laplace transform, we can make our circuit analysis just a little bit easier, kind of save us a little bit on that algebra. So that kind of does it for our discussion of the Laplace transform. I know I've had you guys watching those Khan Academy videos. I think those are great. He does a much better job of explaining the mechanics of the Laplace transform than I can do. So that kind of does it for that. And we're going to move on next into chapter 13, where we're actually going to start to take that Laplace transform concept and apply it to our circuit analysis in a much more hardcore kind of way. Kind of like in the same way we sort of took phasors and kind of walked through the different how they apply to the different circuit analysis techniques. We're kind of going to do the same thing now. We're going to do it with the Laplace transform and kind of go through and see how does the Laplace transform apply to all of our different circuit analysis techniques. And as you'll see, it's a lot like the phasors were in our sinusoidal steady state analysis. And we're kind of still building towards the punchline of the course, which is designing filters and frequency responsive circuits. So that's it for this one. As always, if you have any questions, comments, or concerns, please let me know. And if not, I look forward to seeing you guys in chapter 13. Thank you.